Alright, let's sketch a possible graph for the following function. F of x is equal to negative x minus 4, x minus 1 times x plus 5. So this is a function, a polynomial function in factored form. And just off the bat, you can notice here that there's a negative on the outside. So we want to look at factored form as f of x is equal to a, x minus r, x minus s, x minus t. And you can notice that because there are three x values to the power of 1, if you multiply them together, right, you should get an x cubed term. Then whatever a is going to be for the leading term is going to be a x cubed. Okay, so this is your leading term. Well, we can notice here that the leading term here is negative 1, so your leading term here should be, like the leading coefficient, sorry, is negative 1 because you have a negative 1 here. So the leading term here should be negative x cubed. Okay, so it tells us that this is a negative odd degree function. Okay, this is an negative odd degree function. Degree is 3, so the degree here is 3, so n is equal to 3. The terms should be n minus 1, right? The maximum number of terms that you would find in a function would be n minus 1, and the terms are basically points of extrema, right? So because it's n minus 1, then we know that the maximum number of terms you should have here is 2, right? You can have a minimum and maximum, or maximum and minimum. Now, because we know that this is a negative odd degree function, this tells us something about our end behavior, right? We know that odd degree functions, if they're positive, it's quadrants 1 and 3. If they're negative, the end behavior should be in quadrants 2 and quadrants 4. Okay? Having said this, now we want to look at our intercepts. Well, specifically our x-intercepts. The reason we look at it in factored form so frequently is because of the fact that our factors are really key in determining our x-intercepts, or our roots, right? Our roots here are r, s, and t, and you can write each root as r and 0, s and 0, and t and 0. Okay? So in this case, we know that if we want to find our x-intercepts, or our roots, you let f of x equal 0. And in this case, you can just solve for it very quickly. Okay, so our x-intercepts include 4, 1, and 5. Okay, negative 5, sorry. 4, 1, and negative 5, right? These are values that will make each of these factors 0, and 0 times another factor will give you 0 for the whole thing, right? So your x-intercepts are 4 and 0, 1 and 0, and negative 5 and 0. Okay, so those are our x-intercepts. Now that we have our x-intercepts, you also need to look at the order of each root, right? So if we're looking at the order of each root, right, I'll look at the root, I'll look at the order, I'll look at the behavior, right? You can notice that all of these are orders of 1, right? If you look at the root 4 and 0, the order here is 1 because there's only a power of 1 on the factor, and the behavior will slice through it. Okay, it'll pass through it. The root 1 and 0 here, there's the order of 1. This also slices through that point as well. And the other point, negative 5 and 0, the order of 1, it also slices through. Okay, so that is our order. And you also want to look at your y-intercept. I'll do it out here. Y-intercept, the y-axis, the graph when it hits the y-axis, the y-intercept. You need to let x equal 0, right? Because we know that the y-axis occurs when x is equal to 0. So we're doing f of 0 is equal to negative 0 minus 4 times 0 minus 1 times 0 plus 5, which is negative 4 times negative 1 times 5. And this is going to give us negative 20. So 0 and negative 20 is our y-intercept. Okay, so now we have our y-intercept, we have a series of x-intercepts, right? Now what you can do is determine your sketch really quickly, right? So I'm just gonna sketch this guy out, right? Once again, we don't need to create a series of units, right? I just want to plot key points. So I'm going to create a sketch here. I'm going to plot my x-intercepts really quickly. So my x-intercepts, we have 4 and 0. Let's say it's right here. Okay, we have 1 and 0. Let's say it's here. Okay, and we also have negative 5 and 0, which is here. Right, it's not drawn to scale, I know, but try to make it as much to scale as possible. This is 0 and negative 20, right? We can understand that it should pass through these points, right? And it should start at quadrant 2 and end off in quadrant 4. Okay, so technically what you should see here, I'm just going to erase that line. Whoops, that's not what I wanted to do. Right, technically you should see this thing ending off in this quadrant, and it should start in this quadrant. Okay, and we know that it's going to hit the y-intercept, right? So there's going to be some kind of maximum point here, right? And we should expect 2 turns because this is a turn, right? We can assume that there's a minimum here, but there's going to be a maximum here. Now we need to find our extrema. Now because this is an odd degree function, we can only have local maximum or minimum. Okay, there is no absolute maximum or minimum. The reason for that is because the domain and range for odd functions, x belongs to a set of all real numbers and y belongs to a set of all real numbers. There's no restriction specifically on the range. This is true for all polynomials, odd and even degree functions, right? However, this will actually vary for even degree functions, right? Because it's odd, there's no restriction. So there is a local minimum at the y-intercept, 0, negative 20. But there is a maximum point that's located in between, so it's going to be located here. We don't know what this value is, right? This is y, a local maximum. It's going to be in between the two x-intercepts. So you can see that the order of the roots were really useful in generating those intercepts because it passes through all these points, right? Well, we need to figure out what this x value of this turn is, right? Excuse me. So we understand that the x value of the turn here should be the midpoint, right? So it should be basically 1 plus 4 divided by 2, which is 5 over 2, which is like 2.5, right? And if you wanted to figure out the y value of the turn, right, we'll call it y turn, so we'll just keep it consistent. Okay, if you wanted to find the y value of the turn or the y value of the local maximum, what you just do is you just do f of 2.5, and you plug it into your function, right? You get negative 2.5 minus 4, 2.5 minus 1, 2.5 plus, plus 5. Okay, and then if you punch this out in your calculator, you'll get about 16.875. Okay, so this is just there to kind of help us figure out where the point is. Right, so this is 2.5 and 16.875. Okay, so that is our local maximum. We have our local minimum, so our local maximum here is 2.5 and 16.875. So we have our local maximum, and we don't have any absolute maximum minimum, and then we figured out our domain range. So this is our sketch, right? And honestly, this is only possible if you guys look at the degree, the turns, right, the intercepts, the order, right? So that's the idea. That's how we can do curve sketching, by gleaming some of this information of polynomial functions.